Hello, my name is Aaron Balke, and in today's video, I'm going to be breaking down my decision tree classification analysis for my master's in data analytics. This assessment was originally using a theoretical hospital dataset to do the analysis, and this presentation you'll be watching was made originally for that assessment, so there may be some assessment-specific questions and answers involved in it. Just be aware of that as you are watching it. I hope you enjoy. Hello, my name is Aaron Balke, and today we're going to be breaking down my D209 Task 2 Predictive Analysis Performance Assessment. For this performance assessment, my research question, follows the same questions and research I've been doing on other performance assessments, which is, are we able to distinguish the high blood pressure and no high blood pressure groups accurately? And the reason I want to split those groups is because from CDC sources, from other health sources, the cardiovascular disease and blood-related illnesses are sitting at around 25-30% of all deaths in the United States. And my hope would be, if we're able to see what causes people to have high blood pressure and which conditions are linked and correlated with high blood pressure, we'll be able to easier help those groups and make a bigger difference by helping those guys out specifically. The previous analysis I have done, it's had difficulty in splitting the high blood pressure and no high blood pressure groups. Specifically, my KNN classifier had a ton of trouble. It was only able to reach around a 50-51% accuracy, so very horrible at splitting those two groups. I did have success with a logistic regression model at an accuracy of 80%, and so my hope would be with this analysis to get above 80% accuracy in order to split those groups effectively and distinguish the distributions. And the reason I believe we need 80% or more is because when we're talking about health-related predictions, we're talking about people's lives, we're talking about finances, that is all twisted in with health. And so these are big, important things for people. And so if we're able to get a model that's only 80% accurate, I don't feel as comfortable with 80% accuracy as I would with 90 or 100%, obviously. But I think particularly with what we're dealing with, we need as high of accuracy as possible. And so that's the question, that's the goal. We want to lower deaths, and we want to lower readmissions, and we want to do all of those things. And through figuring out why people have high blood pressure and what conditions are related to high blood pressure, we should be able to alleviate that. And so we're using a decision tree classifier for today. It was chosen over random forest because the main plus of a random forest decision tree classifier is that it provides functionality that removes or limits the overfitting problem that a decision tree classifier would have. So that would be the plus of a random forest classifier. But in our situation, from my experience with this data set in our specific high blood pressure feature, we haven't really had an overfitting problem yet. Every time we've had a problem, it's always been underfitting. And so I don't see a reason of using a random forest classifier, since it wouldn't alleviate a problem we're having, and it would just add needless complexity to our model. So that's the reason I chose a decision tree classifier. A decision tree classifier, it follows a logical path of questions you ask about the data, and then from there you go from question to question and you're able to find a predicted label for that data. In our situation, you would go down and there would be a question such as, is male? And if they are male, you would go one direction, ask another question. If they weren't, you go a different direction and ask a different question. And as you go down this tree, you'll finally hit a either high blood pressure or no high blood pressure label at the very bottom on the leaves. And those would be the expected outcomes and predicted labels of our model here. The one assumption of a decision tree classifier is that at every node there is a binary option. It's either this way or that way. There's only two ways you can go. And while that works for many cases, the complication comes when there's a little bit more nuance and there's more options at where you would think a node would be. And the way I like to think about this is with like animals, for example. If you have three options like a bird, dog, and a cat, the first question would be, does he have four legs? And if he has four appendages. And if the answer is yes, then all three of those options are possible. In order to differentiate and in order to have binary options, you would have to add another layer to it, another bit of depth to it that would ask, does he have wings or in order to split those down into binary options. And the problem with this is the more layers you add and the deeper the model gets, the more susceptible to overfitting it can become. And so the important thing when we're working on this model is we have to make sure that the model is fitting generalized nodes and not getting super train data specific ones. We want to make sure we're not overfitting at all. So that's something we have to keep in mind with a decision tree model. For this analysis, we're going to be using Python version 3.10.9. We're using Python because it is a very straightforward programming language. There's not a lot of crazy syntax. It has a bunch of library support. We're going to have access to pandas, NumPy, sklearn, and that will automate a lot of the hard work we're going to have to do today. And Python's the one I'm most familiar with, so that's the other reason. We're also using Jupyter Notebook version 6.5.2. We're using Jupyter Notebook because of the checkpoint functionality, which will allow us to save the state of our models and go back to that state whenever we would like. And so we don't have to keep running the models, particularly with this one when we get into the search grid CV, the grid search CV stuff, when we're running many models at a time to try to find the optimal one. This is a very intense computing stuff, and so we want to save that state and not have to run that every time we open up this Jupyter Notebook. So that's the power there. We're also using pandas. Data frames are awesome, so that's what we got pandas for. NumPy we got in here. There's some more complex computing that NumPy can fix for us. And we also got sklearn in here. sklearn is going to be doing most of the heavy lifting. We got the train test split in here. We have some metrics to evaluate the model. We've got the decision tree classifier object itself for this analysis. And we also have the grid search CV in order to help find the optimal model. So sklearn is going to be doing a lot of heavy lifting here. When it comes to data preparation, the nice part about decision tree classifiers when compared to previous methods is it is not a distance-based analysis. It's not something that requires us to remove insignificant features. It's not something that we have to get in here with p-values and deal with multi-collinearity. So we don't need to get in here with variance inflation factors, all of that fun stuff. The only big things we have to do is convert data types to be correct and create dummy variables for one-hot encoding. And the one-hot encoding takes a categorical variable with multiple values, multiple categories, and converts each of those categories into their own features. And so that allows us to put the numerical data into the model and not just have the string categories. We have a list of variables here. I'll talk about a little bit later at the end, but the important thing that's different from this compared to all my previous models is the addition of additional charges as a feature. And we will see that will be very important later on. What we got here, this is what we have to do for data preparation. So first thing, we'll be dropping unused features. There is just a bunch of additional ones that we don't need, and so that's location-based stuff, that's survey-based stuff, so we'll remove all of that from the data set. We're also going to convert data types, so objects into categories, booleans into boolean strings into numerical values. So that's the string yes, the string no into 0 or 1. We're going to create dummy variables. That's converting the categorical features into binary numerical features. And then finally, we're going to split the data into the independent and dependent variables, two separate data frames. And so that's what we got going on here. We got the standard imports, pandas, numpy up here, and then we got the fancy sklearn ones. We have the train test split that splits our data into training and test data frames for evaluating the model. We also got grid search CV. Grid search CV will be used for cross-validation, and that will be taking our training data, splitting it into chunks in order to find the optimal parameters. Then we got the decision tree classifier in here. That is the main object, the main model object. And then we got a couple metrics in here in order to find the accuracy of the model and other stuff. This is us dropping the features here. I better run this thing. Restart and run all. Gotta make sure it all works, you know. Dropping all the features. This is stuff I've just pulled from previous. Okay, there we go. It's probably going to take a minute, but this is just stuff I've pulled from my previous performance assessments, all the same. The only thing that's changed is I've added additional charges to the numerical variables. And we also got the dummy variables down here for the one-hot encoding. And so that just converts the categorical into individual features. And then we split the data into the high blood pressure dependent variable and the independent variables, everything else, into a separate data frame. We then export all the data down here. We got two separate CSVs, one as the X and one as the Y, the independent and dependent variables. And then we split the data into the training and test data. And I used a 20% test, 80% training set. I've always done either 20 or 25, so figured that was a good size. And now for the decision tree classifier itself. In order to use the decision tree classifier, the first thing we're going to have to do is define the ranges of the hyperparameters that we want to test for. We're going to use a grid search cross-validation in order to find the most optimal parameters, but we do have to set a range for the grid search CV. And what I decided to do was a max depth of 1 to 20. That seemed like a good range there. That's how many levels into the tree you go, you know, how many questions you ask along the way. And then minimum samples leaf we have set here. This was trial and error, but I did 0.01 to 1 and then increment 0.01. So it's 0.01, 0.02, 0.03, all the way until 1. And so that was as big of a range as I thought was adequate in order to find the best one. So we define the hyperparameters, the range of those hyperparameters we want to test for. We initiate the decision tree classifier and the grid search CV. We have the grid search CV by default has a 5 folds, and so it splits the training data into 5 parts fold, and then the rest are training, and then you train it on those 4, figure out using the test one how accurate it is, and then you do that for each other one. You set a new one to the test and then train it on the other 4. You do that for all 5, and then at the end you average a score out as the score for that parameter set. And then after getting the average score for all of those parameter sets, you have a optimal model, whichever one has the best score. We are using the area under the curve as a metric for the scoring, and we are using the end jobs here of -1 just says use as much of the CPU as possible. So that's what that's doing in here. Otherwise, this would take forever. Speaking about taking forever, it looks like we had an error. Oh. We better import matplotlib. Plot as plot. And I think this is so embarrassing. There we go. There we go. They all work. Don't be removing imports before you run this. Alrighty. So we have the grid search CV, which takes all of that, scores, finding the best set of parameters, and then we fit the training data to it and get the best set of parameters and best decision tree classifier, which is this here. And then we run a prediction on the test data and get a predicted set of labels. In our situation with trying to get the high blood pressure, the most optimal set of parameters is a max depth of 5, so that's 5 layers in the decision tree, and the minimum samples leaf is 0.02. So we ran the predicted value earlier, and in order to evaluate the accuracy of this model, we're going to use a confusion matrix, a area under the curve, metric, and visualization, and then we are also going to use a mean squared evaluation at the end, a mean squared at the end. And so the nice part about all this is it's the same stuff I used for the KNN and all. I was able to just copy and paste that here. The confusion matrix is also looking very promising. We want everything, or as much as possible, to be in this first set here and this top left corner and bottom right corner. These are values that are actually true and predicted to be true, and values that are, actually false and are predicted false, and then values that are true and are predicted true as well. And it looks great. We have only 29 options that are 29 records that are not accurately put in the right section. There's only 29 out of 2,000 that were false positives or false negatives. And so we're able to also see from the accuracy, precision, sensitivity, specificity, F-score metrics that we're sitting at an accuracy of 99%. So this is a much more accurate model than my previous ones, even the logistic regression model, which was 80%. This is way, way better when it comes to splitting those distributions, the distributions of the high blood pressure and no high blood pressure groups. Another visualization we got here is the area under the curve visualization. With a area under the curve, the worst possible case is just a straight line from bottom to top right corner, from bottom left to top right. And then the best is if you pretty much have a straight up vertical line and then a straight horizontal line. We want to try to get in this corner, this top left corner, as much as possible. And we are really, really close to having just a 90-degree angle, which is awesome to see. We have a AUC value of 0.9988, which is so close to completely accurate. So that's our area under the curve visualization. And then we also have our mean squared error of 0.0145. I was trying to do some research on the mean squared error, and it's required by the rubric. However, I can't see. It seems to me from everything I researched that it doesn't work that well for the binary classification of this decision tree. It sounds like that's not really the metric you would use. Either way, it is a very low number, which is what you're trying to go for with a mean squared error. Including it in here for the evaluation, however, I do think the confusion matrix and AUC visualization provide more insight into the model. Either way, all three say we have a great model here. Great model. Let's talk about the limitation of this model. And in order to speak on the limitation of this model, we have to talk about what it took to get to this point of a super accurate model. And I ran this model many times and was having a terrible time gaining an accurate model. I was still gaining around 50% accuracy. It was not doing better than my KNN classifier, which was horrible. And the reason for that was I was not including the additional charges feature. And the additional charges feature is everything to this model. This feature is required for this model to be accurate. And so the limitation of this model is that it is so heavily based on this one feature, and the feature itself, the additional charges feature, is something we can only get after a admission of a patient. And so the problem with this analysis, this decision tree classifier, is that yes, it's almost 100% accurate, but we can only use it in situations that occur after the initial admission. We can't use it to make assumptions on a patient before they come in. Like if we had some sort of survey, a pre-admission survey, we can make a bunch of assumptions about high blood pressure and all from that, if this model didn't require the additional charges feature. But since it requires the additional charges feature, we have to wait until that patient is charged and after their initial admission in order to have this accurate of a model. And so that is the one limitation with this model, is using that feature, and that feature is required for it to be accurate. And following that line of reasoning and dealing with that limitation, we fall into my recommendation, which is that we do use this for predicting and classifying patients with high blood pressure, but we can only use it in situations that occur after the admission. After the admission, this is a great thing to use. We can get pretty much 100% accuracy, no problem whatsoever, but we can't use this beforehand, obviously, because we don't have the additional charges feature. And so for those initial admissions, for more immediate situations, I believe the logistic regression model I built previously that didn't use the additional charges feature would be better suited. We would only have 80% accuracy, but that's way better than this model without the additional charges feature, which would only be around 51%, which is not good enough, And so this one would be great for anything after the initial admission. And the main example I thought of when it came to using this model was imputing data in our model, the high blood pressure feature in our data set, because if we have missing high blood pressure values, yes or no, the records in our data, then previously what we had to do was we had to use some sort of average, like most frequent, the median value, the mean value. We had to use, well, I guess with binary it wasn't a mean value, but we had to use those sort of averages in order to fill in the missing data, or we had to remove those records from the data. Now, though, we have a decision tree model that's able to predict what values should be put in there with 99.88% accuracy, which now you're able to create a data set that has we don't have to remove as many features when we do future data analysis. We have a model that can impute data into our data set, so we don't have to remove data, we don't have to use averages that could be inaccurate. And so that's the main value of this model I see moving forward, and the main place I see this being used. That is my decision tree performance assessment, my D209 Task 2 predictive analysis. I hope you enjoyed and hope you have a good one. Thank you.